Hello, honors pre-calculus students. So we're going to spend 3 days talking about learning target 2, which is piecewise functions. So you're going to learn how to evaluate them and graph them. And if I give you a graph, can you work backwards and come up with a function? All those things. So you've probably seen these before. So a piecewise function is just a function which is broken up into pieces. This first example has 3 different pieces. So the items on the left-hand side are the actual pieces of individual functions. So here we got a line with a slope of 3 and a y-intercept of -8. Here we have just the number 2, which would just be a flat line, just a horizontal line with a slope of 0. And here we've got a third line with a slope of 1/2. So these lines come in and out of existence based on the domain. So this first line only exists between -2 and 5, including 5, but excluding -2. So it's just a portion of that line. And this flat line only exists between 5 and 9, between the x values 5 and 9. And the final one exists forever. It goes on, but it begins at +9 and it continues on. So it's worth noting also that this is also a function. There's no single x value that would produce 2 different y values. For example, 9, if x equals 9, you're on this portion because this is x is greater than or equal to 9. 9 just barely misses the cutoff here. 8.9 or 8.99 is included here, but not 9 itself. X, for the middle section, x has to be less than 9. So continuing on that idea, f of 0. Well, 0 as an x value is in between -2 and 5, so it belongs to this portion. So it's 3 times 0 minus 8. This happens every year. There's a student half listening, and they will plug in 0 for all 3 parts, all 3 pieces, and get 3 different y values. So not only are they royally screwing this up right here, but they're actually trying to show us that it's not a function. If you plug in 0 for x, you should only get 1 answer, not 3 different answers. So again, x value is 0, and 0 is between -2 and 5. So it belongs to this domain, which belongs to this piece, 3x minus 8. Well, what about 6.7? As an x value, 6.7 is in between 5 and 9, so it belongs to this output, which is just 2. So this is the easiest problem in the world. F of 6.7 is just 2. No math needed. What about f of 100? Well, 100 is greater than or equal to 9. So that means it belongs to this piece. So I take 1/2 times 100, and I get 50. And f of -10, well, -10 is not greater than 9. -10 is not between 5 and 9. And -10 is not between -2 and 5. So -10 is nowhere in the domain, so therefore it's just simply undefined. F does not know what -10 is. Can you look at a graph and evaluate and get an actual y value if I give you an x value? So here, this is a very common piecewise function, especially next year in calculus. So you've got a parabola, and the parabola has an infinite amount of ordered pairs, but one ordered pair, so -2, -2, was plucked out, and in its place was this ordered pair, -2, comma, +2. So this is a piecewise function. You've got a parabola, which is the big piece, and then this single point. Well, what is f of -4? When x is -4, you happen to be on the parabola part, so that the result is +2. F of -2. Well, -2 is right here, and -2 is the only x value that isn't on the parabola. There's an open circle there, but -2 is up here. So when x is -2, the result is +2. And f of 1, well, we're back on the parabola. When x is 1, you're way up here. It looks like your y value is 7. Also worth mentioning that if you were to draw this graph, you would have to lift up your pencil, which means it's discontinuous. And this graph, this function happens to be discontinuous at one point only, -2. When x is -2, that is the one point of discontinuity. Another example, you've got a parabola and a line. Well, what is f of negative 8? Negative 8 as an x value is on the parabola part, and the result is negative 2. F of negative 5. Well, here's negative 5, and it looks like you should be on the parabola part, but you're not. At negative 5, there's an open circle. And looking up and down, when x equals negative 5, I don't see another y value. So what's your conclusion? What is f of negative 5? It is undefined. Same thing with negative 3 and negative 4. F of negative 3, the graph is nowhere to be seen when x is negative 3. Same with negative 4. F of 0 is 3. That's on the linear part. Also the y-intercept. And f of 2 is also on the linear part. That when x is 2, looks like the result is 0, which is called the x-intercept. This graph, this function happens to have 3 zeros, here, here, and here. 3 real x-intercepts. Can you evaluate them algebraically? This is like our previous example. We have a function f, which looks like it's a parabola, to the right 6 and down 1, and then just negative 1. Well, under what conditions determines which piece am I in? This part of the domain, I guess you call this the subdomain. So when x equals 4, the result is negative 1. And when x doesn't equal 4, the result is the quadratic. So most of this function is the quadratic because most numbers aren't 4. And on the one special occasion when x does equal 4, the result is just negative 1. So let's just get this one out of the way. F of 4 is just negative 1. But f of 0, well, 0 is not 4. So since 0 is not 4, it belongs in this piece. So I would take 0 minus 6 squared minus 1 and get 35. And f of 2 is not 4, so it belongs in this portion. And 2 minus 6 squared minus 1 is 15. The second function here has a piece of a parabola only when x is less than 3, a negative 4 when x is exactly 3, and negative 3 when x is greater than 3. So can you see that the domain for this whole function is all real numbers? Everything is accounted for. Every number less than 3, every number greater than 3, and 3 itself. So every number is accounted for. Well, what's g of 3? G of 3. When x is 3, the result is negative 4. What about g of 512? 512 is not less than 3, so I'm not doing this one. 512 doesn't equal 3, so I'm not doing this one. 512 is greater than 3, so I'm doing this one. G of 512 is negative 3. And g of 2, well, 2 is less than 3, so I'm doing this piece. So this brings me the most work. I have to take negative 1 times the input, 2, minus 1 squared, and then subtract 3. Let's see if I did my math right. 2 minus 1 is 1. 1 squared is 1. That becomes a negative 1. Minus 3 is negative 4. Next, can we work backwards? This is a great skill if you could do this. And we did the transformation section first so that we could do problems like this. How do you express this function? Well, it's a parabola, first of all. The parabola is the most significant, it's the most dominant piece of this piecewise function. In fact, what's the parabola's domain? It covers everything down to negative infinity, everything up to positive infinity, includes every x value except for, it looks like when x is negative 2, this parabola does not exist. And to write that, we get to write, with piecewise functions, we get to write the easier version. We could just say x does not equal negative 2. So when x doesn't equal negative 2, I'm on this parabola. Well, what is the function? What is the explicit equation of this parabola? Well, Parabolas begin, their parent function is centered at the origin, 0, 0 for a vertex, but this vertex is to the left 2 and down 2. So I moved to the left 2 and I moved down 2. Is there a vertical stretch? It doesn't look like there is, because in the original parent function, if I go over 1, the result is up 1, because 1 squared is 1. And if I go over 2, the result would be up 4, because 2 squared is 4. That's the same thing that's happening with this parabola. From the vertex, if I go over 1, I go up 1. And if I go over 2, I do go up 4. 1, 2, 3, 4. So there is no vertical stretch here. It's just simply to the left 2 and down 2. So x plus 2, moving it to the left, squaring that, making it a parabola, and minusing 2, sinking everything down 2. How do you do this? Well, there's actually lots of solutions here. This y value is positive 2, and it occurs when x is negative 2. So you could, if you wanted to be kind of tricky, you could say, let's see here, 4 plus x would be a correct answer. Why? Because I could have this little piece be 4 plus x. Now this is a line with a slope of 1 and a y-intercept of 4. But this would work because when x is negative 2, you have 4 plus negative 2, which results in what? It results in 2. And that's all I need. I just need it to result in 2. But let's just keep things simple. See if I could delete this for goodness sake. And you could just write this for full credit. This is probably this is preferable. Just write down 2. There's just one little ordered pair here. The y value is 2. And when does that occur? When x is negative 2. So when x is negative 2, the result is 2. When x isn't a negative 2, the result is the parabola. This one, you've got a parabola and a line. Let's do the parabola first. The domain of the parabola. Notice it's to the left, it's less than negative 5, and it doesn't include negative 5. So we are saying x is less than negative 5. The other one, the line, is everything greater than negative 2, but not including negative 2. Now the rest is just coming up with these functions. Let's do the parabola first. Remember, the parent function of a parabola is centered at 0, 0. This one is a vertex of negative 8, negative 2. So you went to the left 8, and you went down 2. And again, there was no stretches. You could see here from the vertex, if you go over 1, you're up 1. If you go over 2, you're up 4. So since this is a quadratic, it's squaring everything it gets. 1 squared is 1, 2 squared is 4, 3 squared would get you 9, etc. There's no vertical stretch. So just move it to the left 8, move it down 2. And make sure you have that square there because it's a parabola. This line brings you back to Algebra 1, which we don't study a lot of lines in this section, in this year, which is kind of a pity because lines are very, very important. They will be popping up to kind of keep your memory fresh, and here's one of those examples. This line has a y-intercept of positive 3, so it's going to end in something, something plus 3. And I just need to determine its slope. And it looks like, well, it's definitely negative because it's going down, but at first I thought it's negative 1, but it doesn't quite look like negative 1. If I look closely, it looks like it goes down 3 and over 2, which is negative 1.5. So the slope is negative 3/2 x plus 3. The last slide for today. There's a lot of information thrown at you here. Can you graph piecewise functions? So you've got this piecewise function has 2 lines. One with a slope of -1, one with a slope of 2. The lines only exist under these domains. So what I would suggest, there's lots of correct ways to do this, but let's just graph this first one, negative 1x plus 3. Okay, so to graph this, I like to graph the entire thing, but kind of like with ghost lines, just with faint lines. For instance, this first one, negative x minus 3. So the y-intercept is negative 3, and the slope is negative 1. So it's going down 1 over 1. And I would just lightly with my pencil kind of sketch that line. And I know that my final answer is only going to include the portion of that line when x is less than or equal to negative 2. So beginning when x is negative 2 and then moving to the left. The other one, 2x minus 7, has a y-intercept of negative 7 and a slope of positive 2. So I put a dot at negative 7, and then I would go up 2 over 1, up 2 over 1, etc. But this line for my final answer only exists when x is greater than 1. So I would start at negative 7 and go up 2 over 1. Now my x value is positive 1. And I would start here with an open circle and sketch my way up, getting this for my final answer.